at a few projectile motion problems. So this one here is page 98. It's sample problem D. So it actually has work written out in the book for it as well. But I just want to set it up with our givens chart and all of that for you today. Okay, so sample problem D says the Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. Suppose you kick a rock horizontally off of the bridge. What is the magnitude of the rock's horizontal and the magnitude of the rock's horizontal displacement is 45 meters. Find the speed at which the rock was kicked. So this is a little bit different than the one that we did yesterday. So let's take a look here. So there's going to be my bridge. Looks kind of like a table. And put some water down there. And then I'm going to draw a rock. Obviously none of this is drawn to scale, but you get the idea. And the projectile is going to come off like this. And it's going to splash into the water. There, okay? I'm going to just draw my picture because we didn't have one before and include some givens so that I kind of know what I'm doing here. So it says that it's going to be kicked horizontally in this direction. So I'm going to just go ahead and draw that initial velocity arrow, and I'm going to mark that as my initial velocity. In this case, it happens to be all in the x direction, so I'm going to label it with an x. It says, I think, I'm going to double check here, that the magnitude of the rock's horizontal displacement is 45 meters. So that's my delta x. I'm just going to go ahead and write down that delta x is 45 meters in that direction, okay? It says that the bridge is 321 meters above the Arkansas River. Again, to be clear, not drawn to scale, but you get the idea here. Okay, all these pictures are going to look pretty similar. So 321 meters above. Now, that's the distance. When we talk about displacement, we're going to have to remember to make that negative. Okay, so that's kind of my setup before I write out my givens. And then I'm going to go ahead and use that givens chart that I showed you yesterday. So we're going to have the x stuff here. So that's going to be delta x, initial velocity in the x, and acceleration in the x direction. Okay, then I'm going to go ahead and do my y stuff as well. So that's delta y, initial velocity in the y direction, and acceleration in the y direction. And I'm just going to fill in as much of that as I can, and I'm going to remember that time is the thing that ties it all together. I'm going to start with the easy stuff. So I know the acceleration in the y direction is negative 9.8 meters per second squared. And I know the acceleration in the x direction is 0 meters per second squared. Again, those are kind of like your free spaces. You know those always in for sure. Because it's a horizontal launch, or a horizontal kick, I guess, is really what we have here. That means the initial velocity in the y direction is 0 meters per second. And in this case, it asks for the speed that the rock was kicked. So in this case, we actually don't know the initial velocity in the x direction. We do know the displacement, though. We know that the displacement in the x is 45 meters. That's where we saw it from the writing, and then we can also put it there. And the displacement in the y direction, we have that 321 meters written down on our diagram. We have to remember, though, that it's going down. Because it's going down, it's going to be negative. So again, this problem is kind of similar to the one that we did yesterday, but in this case, they're really only asking for one thing. They're asking for the speed, and so we see that that's right here, okay? That's the thing we want to know, but we can't solve for the x stuff without solving for time first. So it's kind of a hidden question in there that we need to find the time first. So we're going to look at our givens. Remember that we set this up so that most of these problems are going to be solved with my very favorite equation. Delta y is equal to VIY times t plus 1/2 AY t squared. We say, oh, is there anything that's equal to 0? And indeed there is. So that initial velocity in the y direction is 0, which makes that whole term go to 0. And now we've got this thing that we can solve for t. You may feel like you've done this before, and it's because you have. We're going to multiply by 2, divide by AY, and then we'll take the square root of all of that stuff. So we'll have t is equal to the square root of 2 delta y over AY. We can plug in our values. So we've got the square root of 2 times delta y, which is negative 321 meters. I'm guessing that this time is going to be a lot higher than the times we've been dealing with before because we're up really, really high. So we're launching from much higher up. So we'll take the square root. I'm going to get my calculator out here. You should get your calculator out too. Don't rely on me. Make sure that you know how to do this as well. So it's 2 times negative 321 divided by negative 9.8. You got to have negatives in there for both of them, otherwise it's not going to work. Okay, and then we get a time, something like 8.09 seconds. So again, that time is a lot bigger, but we're talking about 300 meters up in the air, so that's pretty darn high. So 8.09 seconds. Now we're not done with the problem, because that's just the time. That's telling us this thing over here, 8.09 seconds, and now we can use that to solve for the x stuff. Same equation. We're just going to write it out again, because we're talking about just the x stuff this time. So delta x is equal to VIX times t plus 1/2 AX times time squared. Again, is there anything that's equal to 0? Yep, indeed there is. That's equal to 0. So now we need to solve this for Vx. The initial velocity in the x direction is equal to delta x over t. So delta x is 45. Plug that in. 45 meters divided by the time of 8.09 seconds. And then we can go ahead and divide that out. 45 divided by 8.09, and you get 5.56. So we'll go ahead and write that down. VI in the x direction is 5.56 meters per second. Two quick things to note, just because it's kind of interesting. One is that if you look at this equation right here, this is just the initial, that's just a definition of velocity, right? If you have no acceleration, which is what we've got, which is kind of cool. The other thing that I want to point out to you so that you're aware is that you've seen us use this equation a bunch of times. You've used it a bunch of times, really. But I don't want you to memorize that, get that stuck in your brain, because in a couple of days, that equation won't be quite valid anymore, okay? So I do want you to go through that process every time so that you understand where that equation is coming from, all right? Awesome. Happy physicsing.